Esperanto Technologies, Shankar Jayaratnam and Raymond Tang. So Shankar is a senior tech lead at Esperanto Technologies, defining and implementing full chip SoC validation methodologies. He's currently working on defining and implementing system software firmware architecture for ET's SoC. Before Esperanto, Shankar was a senior tech lead in an Intel CPU team, defining more efficient development strategy for Intel's future generation CPUs. And Raymond Tang, he's engineering director at Esperanto Technologies, responsible for the company's agile verification effort worldwide. He's also responsible for verification methodology and infrastructure. Before Esperanto, Raymond was the design verification director for Soft Machine Inc., managing 2 generations of successful tape-out, leading to the startup's successful sale to Intel. Before that, Raymond led multiple CPU projects in other corporations, including Intel, Sun, Oracle, NEC, and Fujitsu. Shankar and Raymond, so please start your presentation.
Okay, can you hear me clearly?
Yes, very clear.
Okay, thank you. So I'm going to share my screen. Hello, everybody. My colleague and I are more than happy to share our experience in using our verification methodology to achieve a high-quality silicon for Esperanto Technologies. So this is our topics today, right? I think the KG already including ourselves, so we are going to skip this one. We are going to look at briefly our supercomputer on chip, the Esperanto's new processor. We are going to talk about the challenges to verification, our methodology, our execution results, followed by the key takeaway. Then we will answer some question. So this one I will skip. Okay. So Esperanto Technology, this is our ETSoC. We call it ETSoC1. Is our supercomputer on chip. This design has over 1,000 RISC-V core, and is mixing of the 2 types, right? So first type we call it the ET Maxion. This is a high-performance RISC-V processor responsible for Linux and software application workload. And the other type is we call ET Minion. This is an accelerator for machine learning computation. We have multiple level of core and caches hierarchy, and we intelligently group them into a system that we call a shire. So each shire, the shire-to-shire communication are done on a huge mesh-style network on chip we call the NOC. So the ET Minion shire is our basic compute block. It's a compute core. And we have other shire as well that actually include, of course, our high-performance high performance Maxion core, include DRAM controller, PCI Express controller, and other IOs. It include a service processor and a lot more peripheral. The chip is built in a TSMC 7 nanometer process, which gave us extreme low power. So I'm going to talk about some of the challenge in verification. So as a new company, every aspect of our project is new to us. That is not only limited to our architecture, right? Our interconnect process, our tool chain, our software stack, the golden reference model, everything is brand new. And as you can see from my previous description, our design is very large. It's exceptionally large with a huge mesh network. That actually introduced lots of parallel events and hard to hit corner case that we never thought of. Since everything is new, we cannot just follow some cascade manner. We decide to embrace our co-development process, right? Our architecture, hardware, software are co-designed together. This methodology actually saves time, but that makes our specification a moving target. And as a verification team, the specification moving target is a challenge. It's very difficult for us. And we saw that the verification effort is going to be a great challenge. So we cannot follow traditional style of verification. We have to be smart on cutting corner, and we have to be smart on finding a way to left shift our project in terms of the schedule. So we invest very heavily on our verification team and our tool. For example, we adopt very early on to use Synopsys ZBoot emulator that allow us to find bug faster, and at the same time allow software team, is not just DV, allow software team to develop the software early on. So it's a team-to-team cooperation. We have lots of collaboration in our company. So I'm going to move on to Shankar to present this.
Yep. So high level, what we're trying to present here is basically the three major platforms that has been used for development. So initial part, what happens is the ISA is not stable, right? As we're building up the ISA, what we have here is what we call a virtual platform. The virtual platform is non-cycle accurate, but it allows us to explore our architecture development. And so we're able to run content on it and expose how the ISA would form, how the ISA would develop eventually. And that allows us to actually rapidly prototype our ISA development using this platform. And then as we move on, as we start developing the RTL based on a Verilog, what we did is we actually used a Verilog simulator from Synopsys called VCS. And here, as you can see, this pretty much allowed us to actually simulate the full chip. As Raymond was saying, the chip is huge, right? Because it's got a huge mesh network, thousands of cores, RISC-V cores, the DRAM controller, the cache controllers. So all this to be able to fit into a simulator and running at that kind of performance, it was really challenging for us. But eventually, I think we did a pretty good job in bringing up the performance. Simulating the whole chip in a reasonable time. And this platform actually was used to actually find most of our hardware bugs, as you can later will show you where were most of the bugs found. But actually, this platform is the one that actually helped us find most of the bugs. And then finally, we have what we call the Synopsys ZBoot platform. And this is actually an emulation platform. It's actually taking the RTL, synthesizing it on the FPGAs on the ZBoot platform. And the way we had used this platform is actually to optimize and fine tune our software because this is actually a cycle accurate model. And it allows us to actually look at the performance of the end-to-end software stack and see how we can optimize the software to hit the performance goals that we had in mind. Okay, Raymond, next slide. Okay, so what is the experience using these three platforms, right? One of the key things is there is number of IPs that were reused across the platform. So example, we had assertions, coverage objects which we could use cross platforms, and that enabling a so-called a cohesive uh, environment allowed us to move from one platform to another platform and port all this so-called verification IP across the different platforms. And then the other one is basically we actually use what we call a coverage-based profile. So what does that mean? So basically, we had a weekly profile that helped us understand where the coverage of the content was actually, and this helped us target like more fine-tuned content as we go along during the project, because we find holes as we profile this, we get the feedback, and then immediately we fine-tune the content to actually target the holes, and so it allows us to accelerate the coverage closure. And on top of that, we had the 24/7 ZeBu running in the background, and that actually helped us achieve the seed count, right? Because it's a high performance emulator, and it ran pretty fast, and so we could achieve like tons of seeds. We will talk about the kind of distribution we have between VCS and ZeBu later, but the gist of this is basically the ZeBu platform allowed us to run like tons of seed, and that's why we got a lot of coverage from. And the second thing is when we built the verification components and the bus functional models for this SoC, what we did is we kept in mind that we wanted high performance, high throughput actually. And so the methodology that we used was we ensured that it's first of all compatible between VCS and ZeBu, and secondly is it allows us to not reduce the performance on both the simulators, simulator and the emulator. And so you can see later we achieve like megahertz range performance on at least on the ZeBu side using all these components. And the fourth part is basically what we call an architecture state checker. And this actually helped us achieve like effective debug, and also avoided the fact that we don't have to have all the tests self-checking, right? Because the architecture checker would actually compare architecturally at an instruction level what the state of the processor is against our reference model. And if there was a mismatch in terms of the architecture, say like the registers or the memory, it will flag it. And so it doesn't continue execution, and it helps us zoom down to where the issues is exactly in a much more efficient way. And finally, the DV environment one of the requirements we had was, hey, we should be able to take the software and run it on a DV environment, and the DV would be able to run use case based content on the same platform without any major modifications. And this allowed us to have a strong correlation or strong cooperation between the hardware and software teams. And that was the key to using these three platforms in a cohesive method. Raymond, next slide, please.
Okay. Okay, so I'm going to talk about our co-development flow. As I say, the software, the architecture, RTL, these are all newly designed here. How do we actually make sure then they converge and actually move in the right direction to the exact same spec? So software team, they start with in the project, they start with a small set of software. Sometimes it's the broken down version of the OS, sometimes broken down version of the microkernel. And the architecture team, they build a instruction accurate ISA simulator, RISC-V ISA simulator. So this is an architecture model. And software use through the virtual platform, verify to make sure the architectural model is according to spec. Verification team, however, we take the architecture model through API that talk to our checker, our Verilog or SIP checker, and with a suite of test suite that either handwritten, some is handwritten, some are random generated, some are microkernel or OS snippet. We run all this against the RTL to verify the system Verilog design is good, and we run it through the VCS simulation as well as ZeBu with the three platforms that Shankar talked about. And this RTL design can be compiled into CBU box anywhere from lower level to high level. We compile this. Software team, they use the CBU model to continue their software development, right? The entire software stack, Linux compiler, benchmark, performance model, power model. Software team has their own validation suite, and they use the CBU box with the RTL to develop firmware. So we are going into this cycle of improvement. Each team, we are hoping that they converge by enhancing each of our model and eventually converge and able to reach a production quality. When the design is in more mature state, software DVD verification is able to take some of the software, entire software, and we use it for bug hunting purpose and further perfect our RTL design. So this is the code development flow. I want to go over our test environment execution process. So we divide our level of testing into 3 levels. Start with unit level, mostly focusing on block and some core and unit level testing. And next level is the Shire. Shire is a collection of core with intelligent systems into one system. That's we have Shire. And ultimately, the goal is to make sure the full chip, right, the full SoC level working. And we break down our verification process into 3 stages. The TE stand for test environment development stage, and the feature bring up stage, and the comprehensive test planning stage. When you look at the blue line here, those are the integration point. Our goal is to be able to jump from lower level verification to the upper level verification as soon as possible. So we handpick the specific feature for bring up to allow us to move into the next level. So I give you some example here. For example, we want to be able to bring up a multi-core verification faster. To do that, we need the ET minion core to be achieving some bring up stage, and the tensor unit be able to achieve tensor computation. We integrate it right away into the multi-core bench. When we want to achieve Shire level testing, the ET minion Shire, we handpick the specific feature from multi-core and the cache hierarchy in order to achieve bring up on the ET minion Shire level. At the same time, we allow the lower level to go into comprehensive test planning to find more complicated bug, right? So we do like this. The ultimate goal is to achieve this full SoC level. For that, this is some of the Shire environment. We have the minion Shire. You have the memory controller. Of course, we have the high performance Maxion Shire. The NOT skeleton is the NOT. Basically, those are the NOT with a whole bunch of router without the Shire. So in the full SoC environment, we have the partial, which might contain anywhere from 2 Shire to 4 Shire, and the full chip is everything, right? So once we are able to integrate the Shire as we go along from 2 to 4, we want to achieve OS booting and running benchmark on the actual CBU emulation model on full chip. When we are able to achieve comprehensive test plan phase completed, our coverage, which is functional coverage and the code coverage, are about 95%. The remaining 5% is very, very hard to hit and taking some time. And once we are able to succeed that, we reach tape out quality. So I want to talk a little bit about how do we scale our CBU. Initially, we have a pair of Shire. We just bring up a pair of Shire. with some stub model. These are fake I/O traffic and the memory controller traffic. We compile that into ZBool with just one box here, one CS4. As when we are able to achieve the shire-to-shire level communication, we begin to add more shire into the box, into the ZBool box. At the same time, we compile in the DRAM and the PCI Express controller IP from Synopsys. We add our surface processor because that is crucial for booting Linux. And we also add the ultrasoft debug interface. So this is to mimic the actual silicon bring up sequence. We want to be able to have maturity on our silicon bring up before tape out. So we're able to mimic that. And eventually we scale up to full chip that actually take up XCS4 box, which as Shankar described, we are able to compile it with our reference model and still able to achieve a megahertz speed. That help debugging and a lot. We are able to narrow down to the exact window for dumping and do debugging there. We also have a cloud-based executor that allow us to dispatch multiple jobs in parallel. So more parallel user can run stimulus on ZBool and at the same time debugging on ZBool. So this is about bug finding and fixing our bug. So in the beginning of project start with 0 bugs, and we are able to, when you see from 0 to about 130 bugs, this is the phase when we do bring up testing. A lot of the feature bring up was brought in there. When that test plan actually exhausted, you see a job. And we launch our random generator and also try to bring up ZBool. And this is the time when you see it's actually jumping from 100 to about 300 bucks here. This is when we are able to declare architectural frozen. So a lot of cycle is spent and bug hunting here. And when architecture frozen, you see even our random generator are exhausted, and you see a drop here. And this period here is coverage closure. We have to go into our coverage report, find those holes. Sometimes we have to tune our random engine. Sometimes we have to actually handwritten some tests to fill those holes. And in that process, we find bug, so it bumps up again. And when you look at this line here, the majority of functional bugs has been found, and we are able to boot OS on ZBool, and you see the drastic come down of bug. So this period is mostly we are finding bug on the SOC top level. We are doing DFT verification. We are doing gate level simulation. We are doing X propagation analysis, power state testing. So those are here. And this is almost half of the project cycle here, right? And the other half, we are going into this typical long tail process. You see, the bug rate is very low, fluctuating in between single and double digit. This is the very extreme corner case, very hard to hit bugs that you cannot achieve on VCS. You mostly achieve on ZBool by running actual software, by running billion cycle of generator and find those. So here we're able to run the full software stack, and also later point, we're able to run end-to-end benchmark. So we're able to left shift the schedule, finding majority bugs in half life of the project. So this is crucial to enable software team to do software development. We want to have a very good idea on how our software behave to make sure we have good software quality before tape out. So Shankar, pass on to you. Hello?
Yeah, can you guys hear me? Can you hear me? Okay. So
Yeah,
this
yeah.
chart talks
Can you
about
hear me?
like the, yeah, I can hear. So this chart talks about the distribution of the content across the platforms. So you see pretty much like what we talked about before, there was there are three platforms which we use. One is what we call the virtual platform in blue, the VCS platform in red, and then the orange is what we call the ZeBu platform. And you can see from top down, right? We started off with when we started off the design, architecture exploration, we had all these handwritten tests. And notice at that point, the main platform that we used was the virtual platform because we were fine tuning the architecture. We are trying to optimize the ISA and also the architecture. And that's why we spend most of the time on the virtual platform. But as the design was being implemented as well, you can see it's going hand in hand. And the VCS platform was used like pretty heavily. And that's why we see the cycles being used between VCS and the virtual platform is pretty high. But at that point, the ZeBu platform was pretty low because we have not got the RTL to a point where it's ready to be ported to ZeBu yet. So it took time to come up. And then after that, as we got the random generators up and running, as Raymond pointed out before, right, the first half of the project, we focus a lot on the random generator, and you can see the distribution of the content, right? Virtual platform was less because that is used to actually flush out the bad seeds. And then once the seats were good, they moved on to VCS, and VCS helped us flush out at least the visibility because VCS was more visible in terms of when we were bug hunting. And then when the health of particular random generator groups were pretty healthy, you can see we moved that towards the ZeBu platform. And you look at the ZeBu cycles, that's like the peak of it, right? And that's where we spend most of the cycles, spending just flushing out all those corner cases and interesting interactions that Raymond was talking about before. And during that point, you see the bug rate is coming down, right? The green shows you how the bug rate is actually coming down, and majority of bugs were found during these two stages. And then what happens is we start going into the software phase, right? We start developing micro benchmarks. These are try to exercise the chip in a way how eventually the full end-to-end software will actually exercise it. And you can see first we use the virtual platforms. We spend a lot of time on that, and then eventually we got some of it to run on VCS, and then the majority of it now went and we ran it on ZeBu. And you can see the bug rate has really dropped at this point. So that shows that pretty much the DV team actually did a pretty good job finding all the interesting bugs. And of course, software, because of use case, we also found like some interesting corner cases. And so that's why you can see the bug rate didn't actually go down to 0, but it's still there. And then finally, the machine learning compiler generated content is the final stage. And you can see a lot of time was spent on the blue part, which is the virtual platform, just to flush out all the flows. And then a bit of it spent on VCS because that's how we used to debug with waves. And finally, we use the ZeBu platform for most of the runs because that's a cycle accurate model, which we use to hand tune and fine tune the performance of the software stack. And so if you look at distribution of the bugs, 75% at the Shire level, like what Raymond talked about, the Shire level is the smallest so-called entity. And then the 20% is what we call the inter-Shire. That means the interaction over the NOC and things like that. And then 5% on the top level, which is the SOC at the system level integration. Okay, Raymond, next slide. Okay, so what is the benefits of our methodology, right? First of all, the original goal was, hey, let's make this scalable across at the unit level, which is the Shire level, all the way to full chip because we didn't want to reinvest into the benches and things like that. So basically from get-go, the technology was like, hey, the same unit level RTL, when I scale it up, can actually go and compile and run the actual full chip. So the same test actually works across the board, and even the environment works across the hierarchies. And secondly is the power analysis and performance validation. That's what we wanted to use to guide the architecture. And so that's why you see very early on, most of the architecture was, and the bugs were actually, the RTL is being developed hand in hand. That's why you see the peak of the bug actually was in the first half of the phase because these two were going hand in hand. So the feedback that we got from the performance tuning, we actually helped fine tune the architecture, and the RTL implementation was going hand in hand. And finally, ZeBu allowed us to actually achieve 31x because if you look at the chart that Raymond showed, there's half and half. So the first half was bug hunting on the RTL side, finding all the corner case bugs, and the second half was performance tuning. And you can see, because we had a year, we could actually, and we didn't even have silicon, right? So imagine that. And so we used actually the ZeBu platform to get about 31% speed up. And just because we were able to get the RTL in healthy enough so that we can actually get the full software stack up and running, plus fine-tuning the software to a point where we know, we could have achieved our goals with that. And finally, we had for the Maxion, right? We had this what we call a co-simulator called the Dromajo. That actually has been open sourced. And so if people want to know more, we have a slide. Raymond, you just want to show next slide. This is actually a open source version of a release from our team. So that's actually all the details are here. It's a pretty high performance co-simulator, which supports our Maxion core. And it actually was able to run some of the spec benchmarks. Okay.
Okay.
Next slide.
Yep. Okay. So to conclude this, I just want to say that Esperanto use parallel architecture modeling, simulation, and FPGA emulation to design and debug our ETSoC1 processor. This methodology help us to find bugs earlier in design process and able to speed up bug fix and software development. We use a full chip emulation that enable the software team to actually develop their software earlier before tape out. Our well-integrated Synopsys IP plus VCS plus ZeBu emulation give us high confidence in our production-ready first silicon. And I would like to thank you all for the audience. I would like to say that say thank you and to remind you that our CEO, Aswif, he is going to be presenting in the coming RISC-V Summit in December. If you would like to learn more about Esperanto and our product, I would urge you to join the RISC-V Summit in December. Thank you.
Thank you very much. Yeah, we have a question from audience. So regarding NOC network on chip, so is NOC designed by a special tool, or do you have a special technology of NOC? Because NOC and share seems key component in your design. Yeah. About NOC and share, do you make special treatment for verification? It seems a kind of special technology for making a constraint random of verification.
Yeah. So our NOC is an IP, and we spend a lot of time tuning our stimulus to verify shire and shire to shire corner cases. So we have our we have our homegrown generator. We actually have two generators. One is homegrown, another one is actually acquired. It's called Vouchik Sting, and we use those special generator to generate cases to hit the NOC case.
Thank you. It looks someone is typing the question, so please wait. Okay, maybe no question from audience or still. Oh, okay. Can you share the status of the SoC with us?
The status of the SOC, I think we want to, of course, we are more than happy to, there will be more announcement from our CEO, Aswith, in the coming RISC-V Summit, right? So we want to focusing on the DV effort, the verification effort here. More information about the actual SOC, stay tuned to our RISC-V Summit in December.
So December 8 from 2:30 p.m. Art Swift will present something special. So please stay tuned. Is there any question from audience? So now is time. So thank you very much, Raymond and Shankar.
Thank you very much.
Thank you.